Good morning, children. Once again, we are back on the same chapter, that is D block elements. We were discussing the transition elements, and one of the compounds we had discussed was potassium dichromate. In today's class, we will discuss the next compound, that is potassium permanganate. So potassium permanganate has a general formula KMnO4. It is prepared by the fusion of pyrolusite. What is pyrolusite? That is manganese dioxide with KOH in the presence of an oxidizing agent like potassium permanganate. This produces the dark green potassium manganate K2MnO4, which disproportionates in a neutral acidic solution to give purple manganate. Okay, so what we are getting, we are having the manganese dioxide plus KOH plus oxygen. We are getting K2MnO4 plus water. Okay, after that we have thrice KMnO4 plus hydrogen acidic medium. Ultimately we have the product as potassium permanganate KMnO4 manganese dioxide plus water. Commercially, it is prepared by the alkaline oxidative fusion of manganese dioxide. That is manganese dioxide by alkaline oxidative fusion followed by electrolytic oxidation of manganate. Okay, followed by electrolytic oxidation of the manganate ion. This is the method by which it is being produced. Okay. Okay, now see, we are going to discuss about the reactions of manganese dioxide. Okay, we are going to discuss the reactions of manganese dioxide. Under this reaction, what we have the manganate ion that is being fused with KOH and oxidized in presence of air. We are getting the manganate ion. Okay, now this manganate ion on electrolytic oxidation alkaline solution actually gives you permanganate. Okay, we get this permanganate one. Okay, in the laboratory, potassium permanganate is prepared by oxidation of manganese ion. It can be your manganese dioxide, it can be your MnO. In presence of peroxide disulfate, it forms potassium permanganate, sulfate ion and hydrogen ion actually comes out. Okay, it is the method by which it is actually been prepared. Okay, after that, just see, next is the properties. Among the properties, potassium permanganate is a dark purple crystalline solid. Its color is very dark and purple crystalline solid. On heating, it decomposes at 513 Kelvin and oxygen gas is evolved. So we have potassium permanganate that on heating gives potassium diamond K2MnO4 plus manganese dioxide plus oxygen. So potassium permanganate acts as a powerful oxidizing agent in acidic, basic, as well as neutral medium. Few important oxidizing reaction potassium permanganate are given below. Suppose I have potassium permanganate, acidic medium, we have taken iodine. Iodine is changed to iodine gas has been evolved. So what is the reaction? We are taking potassium permanganate, we are taking iodide salt. In the iodide salt, it will give you iodine gas, right? After that, we have manganate ion that on reacting with iodide in presence of hydrogen ion, we get MnO2 plus iodine plus water. Okay. Now it also changes ferrous to ferric ion. Suppose I have ferrous sulfate solution. In that ferrous sulfate solution in acidic medium, we have taken permanganate. So what happens? The ferrous ion is changed to ferric ion. In this reaction, what we see that the ferrous ion is changed to ferric ion. Oxalate to carbon dioxide. Suppose I have the manganese ion that is made to react hydrogen ion, and the oxalate ion will gradually change to carbon dioxide ion will gradually change into carbon dioxide. So we have the manganate one and oxalate ion in presence of hydrogen ion. We get manganese plus 2 carbon dioxide plus water. After that, we have hydrogen sulfide to sulfur. So MnO4 plus 8 hydrogen ion plus 5 electron, that changes to Mn plus 2 plus water. So ultimately what is happening? Hydrogen sulfide is oxidized to sulfur. Okay, hydrogen sulfide oxidized to sulfur, or this we can say this sulfur actually rings, they comes out. Next, the reaction is from sulfide salt is changed to sulfate salt. Sulfide salt is changed to sulfate salt. That is, we have the manganate ion that is made to react with hydrogen ion. In presence of 5 electron, we get manganese plus 2 plus water and oxygen. In this way, we have this type of reaction. I'm giving you 2 minutes time, children. Just copy down this reaction. After that, we have next reaction, that is changing of nitrite to that of nitrate ion. Okay, that is, it changes nitrite to that of nitrate. In this reaction, what happens actually? See, we have the nitrate ion, right? Nitrate ions. Here we have potassium permanganate. In acidic medium, the potassium permanganate changes to manganese plus 2. Manganese plus 2 reacts with a nitrate ion in presence of water, which changes to nitrite. So what is happening? Nitrite ion changes to nitrate. Okay, this is the ultimate reaction. Here we are having the ionic equation. Okay, I'm giving you 2 minutes time, children. Just copy it down. I hope you have copied it. Okay, after that, we are moving to the next reaction. In neutral or faintly alkaline solution, potassium permanganate oxidizes iodine to iodate ions, which is oxidizing iodine to iodate ion. As you could see that we have the manganate ion. Manganate ion is made to react with water, and ultimately manganate ion changes to manganese dioxide. Iodide is changed to iodide salt is changed to iodate. IO3 is the iodate ion. IO3 minus is the iodate, and in this way the reaction takes place. The manganate and the dimanganate are tetrahedral, and the green dimanganate is paramagnetic with one unpaired electron, but the purple manganate is diamagnetic. So just remember, manganate is diamagnetic, but dimanganate is paramagnetic in nature. So what is the nature? We know that manganate is diamagnetic, but paramagnetic is actually diamagnetic in nature. So but we know that the dimanganate is paramagnetic. On the other hand, manganate is actually diamagnetic in nature. One is paramagnetic, other is diamagnetic. I'm giving you 2 minutes time, children. Just copy down the structure of the tetrahedral manganate ion. See, both the manganate ion is tetrahedral and the permanganate ion is also tetrahedral, but the difference lies is that the manganate ion color is green. On the other hand, permanganate ion, the color is purple. Okay, this is green and this one is purple. In case of manganate ion, there are two O minus ion. Here, this one O minus ion. I hope you have copied it, children. Okay, after that, we are moving to the next part of the chapter, that is the inner transition elements, or that is called the F block elements. They are called the inner transition elements, or they are called F block elements. They're also called as lanthanides and actinides. So we can say that the inner transition element consists of lanthanides and actinides. They are characterized by the filling of the F orbital. Why are they called inner transition? Because they are already present inside the transition series, and in this elements, electron filling takes place in the f orbital. In this, electron filling takes place in the f orbital. Now, the first series we have is the lanthanide series. Under the lanthanide series, the series involves the filling of 4f orbitals following lanthanum. That is, lanthanum is La, whose atomic number is 57 and is called the lanthanoid series. There are 14 elements in the series. Now, starting with cerium 58 to lutetium, the lanthanides are actually having these characteristic features. They are highly dense metal. They are highly dense metals. So first of all, we are starting the lanthanoids. Under the lanthanoid series involves the filling of the 4f orbitals following lanthanum, whose atomic number is 57. It is called as lanthanoid series. There are 14 elements in the series. Now, starting with cerium 58 to lutetium 71, the lanthanoids are highly dense metal. They have high melting points and they form alloys easily with other metals. They are soft, malleable, and ductile with low tensile strength. These are some of the uniform characteristics of these elements. After that, the oxidation state, most characteristic oxidation state of the lanthanide element is +3. Some of the elements also exhibit +2 and +4 oxidation state. Some of them exhibit +2 and +4 oxidation state color. Some of the trivalent ions of lanthanides are colored. This is due to the absorption in the visible region of the spectrum, resulting in A-phase transitions because they have partly filled orbitals. Then we have the magnetic properties among the lanthanides, lanthanum +3 and lutetium +3, which have 4f0 and 4f14 electronic configurations, are diamagnetic, and all the other trivalent lanthanide ions are paramagnetic in nature because of the presence of the unpaired electrons. So, because of the presence of unpaired electrons, they actually just show the magnetic property. So, oxidation state, we know that oxidation state is +2 and +4 color. Some of the trivalent ions of lanthanides are colored. This is due to the absorption of the visible region of the spectrum, resulting in A-phase transition because they have partly filled orbital. Magnetic properties among lanthanide, lanthanum +2 and lutetium +3, which have 4f0 and 4f14 electronic configurations. They are diamagnetic, and all the other are trivalent lanthanide ions and are paramagnetic because of the presence of unpaired electrons. They are paramagnetic because of the presence of unpaired electrons. Okay. Reactivity. All lanthanides are highly electropositive metals and have almost similar chemical reactivity. All of them actually are highly electropositive metals and have almost similar chemical reactivity. Then we should discuss about lanthanoid contraction. What is lanthanoid contraction? In lanthanide, with the increasing atomic number, the atomic and the ionic radii decreases from one element to the other, but the decrease is very small. This decrease in atomic size is called as lanthanoid contraction. This decrease in atomic size is called as lanthanoid contraction. Okay. This decrease in the atomic size is called as lanthanoid contraction. I'm giving you 2 minutes time, children. Please copy it down. Then we'll move to the next part of the chapter. Okay, I hope you have copied. After that, I'm turning the page. Here we have, see, just try to understand the lanthanoid contraction actually occurs because of these lanthanides. As the atomic number goes on increasing, size decreases. That is, for every additional proton in the nucleus, the corresponding electron goes into a 4f subshell. That is, it goes inside the inner shell, which is too diffuse to screen the nucleus as effectively as the more localized inner shell. Hence, the attraction of the nucleus for the outermost electron increases steadily with the atomic number, increases steadily with the atomic number. Uses of lanthanide. The pure metals have no specific use, so they are used as alloys or as compounds. An alloy of lanthanide is used for making mismatch metal, which consists of lanthanides and iron. Okay. Now we have steel that is mixed with lanthanum, cerium, and promethium. Lanthanum, cerium, and promethium and neodymium is used in the manufacture of flame throwing the tanks. The lanthanoid oxides are used for polishing glass. Neodymium and praseodymium oxides are used for making the colored glasses for goggles. They're used for making colored glasses for goggles. Okay, now cerium salts are used in dyeing cottons and also as catalyst. Now, lanthanoid compounds are used as a catalyst for hydrogenation, dehydrogenation, and petroleum cracking. Okay, these are the simple uses we have. Now, pyrophoric alloys are used for making tracer bullets and shells. After that, we will discuss about actinoids. Now, the question comes, what are actinoids? Actinoids are the elements following the actinium series, that is from atomic number 89 up to lawrencium atomic number 103. So, actinoids are those elements that are from actinium 89 up to lawrencium, which is 103. Okay, and are called actinoids. The actinoids are highly dense metal with a high melting point and forms alloys with other metals. High melting point and it form alloys with other metals. They are silvery white metals which are highly reactive. They are silvery white metals and which are highly reactive in nature. Okay. Now, electronic configuration. The actinoids involves the filling of 5f subshell. Actinium has the electronic configuration of 6d17s2. From thorium and zirconium 90 onward, they have the 4f orbital which get progressively filled up. Oxidation state, generally they have +3 oxidation state is preferred in actinoids. The elements in the first of actinoid series, they actually frequently exhibit higher state. For example, the maximum oxidation increases from +4 in thorium to +5 in +6 and +7 in case of Pa. Uranium and neptunium respectively, but decreases in the succeeding elements. Color. The actinoid ions are colored. Magnetic properties. Many of the actinoids are paramagnetic in nature. Reactivity. They are highly electropositive and form salts as well as complexes. Many of the elements are radioactive in nature. Okay, many of the elements are actually radioactive in nature. So these are some of the important oxidation state, color of these elements. The actinoids ions are always all colored. Magnetic properties. Many of the actinoids are paramagnetic in nature. Reactivity, they are also highly reactive, electropositive, and form salts as well as complex. Uses. Now, thorium is used for the treatment of cancer and is incandescent gas mantles. Uranium is used in glass industry, textile industry, in medicines, and as nuclear fuel. Plutonium is used in atomic reactors and in atomic bombs. Okay. These are some of uses of actinide. The first one is thorium. It is used in the treatment of cancer and is incandescent flame. Now, uranium is used in the glass industry as well as the textile industry, in medicines, and as nuclear fuel. Plutonium is used in atomic reactors and atomic bombs. Okay. After that, see, we have next one, that is a comparative study of lanthanides and actinides. A comparative study of lanthanides and actinides that we are going to discuss over here. See, what we know, that lanthanides are those elements that have 4f orbitals is progressively filled. Actinoids are those elements which have 5f orbitals is progressively filled. So here we are studying a comparative study of the actinide as well as the lanthanide. Lanthanides are those elements where the filling of orbitals takes place in the 4f orbital. In actinoids, filling of orbital takes place in the 5f orbital. Now, Now we have the +3 oxidation state is most common along with +2 and +4. Here they show +2, +3, +4, +5, +6 and +7. So just remember, lanthanide's oxidation state is restricted to +3, along with some of them +2 and +4, but actinoid they show from +2 till +7 with +3, +4, +5 and +6. Only promethium is radioactive. Here all the actinides are radioactive. Only promethium is radioactive. All of them are radioactive in nature. They are less reactive than actinoids. They are less reactive than actinoids. They are more reactive. Magnetic properties are less complex. Magnetic properties are much more complex. So magnetic properties are less complex here. Magnetic properties are much more complex. Okay, these are some of the basic differences between lanthanides as well as actinoids. Okay. Is this part now clear to you, children? I'm giving you 2 minutes time. Please copy it down. After that, we'll move to the next part of the chapter. That magnetic properties are much less complex. Magnetic properties are much more complex in case of actinoids. I'm giving you 2 minutes time, children. Please copy it down. I'm giving you 2 minutes time, children. Just copy it down. So here we finished this chapter. So we have finished the D and the F block elements. So that finishes your whole syllabus of class 12. If any doubts are there, you're always welcome to call me, or you can message me in WhatsApp. Thank you, children. Bye.